on your right side.
Hi, Haley. Okay. Excuse me. As we get started, let me say a couple of things. I'm going to go over a couple of problems from the test that gave a number of people problems because I want to show you basically how to do those and where you guys ran into trouble. But I also wanted to let you know that I am posting today a quiz on nomenclature. It's going to be a video quiz. I'm going to ask you to go to a website that allows you to do random practice problems in naming and writing formulas. The idea is for you to, the instructions will tell you what settings to use. And the idea is for you to be able to submit a video within a time limit that has, 10 correct answers. You can do it as many times as you want, film your best one, whatever, but it's a 10-point quiz and it should be turned in by the end of this week. So you can do it as many times as you want. There will also be a quiz on Thursday on chapter 6, which is what we're working on now. We'll finish that by the end of today. So that's really 2 quizzes this week, but one of them is to be done on your own time, and you can do it as many times as you want. If you have any questions, certainly you can give a shout out. Okay, so a couple of things I wanted to talk about on the test, and then I'm going to go over a couple of the problems from that third part. One of the issues for many of you was that we were using unusual units in that we were asking you to report things in nanometers, or we were asking you to report things in megajoules, or we were giving you frequencies in kilohertz. There was a reason for that, and that reason is not just that we wanted you to get practice doing conversions in the SI system, although it never hurts to get practice. The issue is that Canvas does not like very tiny exponents. And many of you in the process of taking the exam were commenting that you would put in your answer and Canvas was automatically making it 0. That's because you had a very small exponent and Canvas makes all of those numbers 0. So I said in the course of the exam, I said, check your units, because that was the issue for most of you. If you did not do the conversion into the units that you were asked for, you ended up with an exponent that Canvas didn't like. So that was where a lot of the problems occurred for some of you on some of those questions. I did certainly give you, if your work showed that it was correct, you got credit, maybe not full credit. I don't remember what I did on, I think at most of the time I gave you most of the credit, if not all of the credit. Except for the fact that you would lose a point for not doing a conversion that you were supposed to do. That being said, let me go to a couple of the problems that gave you some issues. Let's see if I can turn this on. All right. One of the first ones that gave problems was this one. A photon has a frequency of 2.25 times 10 to the 16th hertz. What is the energy in megajoules, excuse me, carried by 6.36 moles of the photons? The equation that you're using here is E equals H times frequency. Very simple, and I think most of you recognize that and got the right formula. What you didn't make note of is that is calculating the energy per photon. This, by the way, your numbers would have been different. This was using a random number generator, so everybody had different numbers here. But I chose one, or I did one with 2.25 times 10 to the 16th hertz and 6.36 moles. So energy is equal to 6.626 times 10 to the minus 34th joule seconds, that's H, times, in this case, 2.25 times 10 to the 16th per second. A hertz is a per second. That equals 1.49 times 10 to the minus 17th joules. But that is joules per photon. So I have to multiply this by Avogadro's number. This was the step that many of you missed. 6.022 times 10 to the 23rd photons per mole. And then I have to multiply that by the number of moles, which in my case, for this particular example, is 6.36 moles. Notice that photons cancels, moles cancels, and I end up in joules. And my answer here is, excuse me, I actually have to have another term, I apologize, but that other term is 1 megajoule per 10 to the 6th joules. So joules will cancel and I'll end up in megajoules. And it ends up with 57.1 megajoules. So the steps that were most often missed in this was multiplying by Avogadro's number. Some people took this term and multiplied it directly by moles. And some people forgot to do the conversion to megajoules or did the conversion to megajoules incorrectly. So that was a problem that many people had. The other problem that most people, if you were having trouble, you had trouble on this one. And this was the one with the threshold energy for an electron from a metal surface. And you were given the threshold energy. Again, this was using a random number generator, so the numbers you had were different, but there is the threshold energy, and this is the energy that the photon was carrying. So the formula is the energy of the photon is equal to the threshold energy plus a term that represents the kinetic energy of the ejected electron. One of the common mistakes in simplifying this equation was people divided both sides by the threshold energy. This is an addition term, so it's E of the photon minus E threshold is equal to 1/2 mv squared. And then you can simplify, you're given the mass of the electron, you can simplify 1/2 times this mass. Now you divide both sides by that and you end up in this case with V squared. If you did the math, you would have V squared is equal to 1.12 times 10 to the 11th meters squared per second squared. Now, since many of you are not familiar with the terms, I want to point out to you that a joule, because energy is in joules, a joule is equal to a kilogram dot meter squared per second squared. So the mass must be in kilograms. You are given this mass in kilograms. So once you divide both sides by this term represented here, 1/2 times the mass, the kilograms are going to cancel and you're going to end up with meters squared per second squared. So when you take that, the square root of that, you end up with the velocity, which in this case was, and then you have to convert that to kilometers. You were asked to determine it in kilometers per second. Remember that this is in meters, and once you take the square root, you can then do a simple conversion from meters to kilometers. And in this case, the answer is 334 kilometers per second. So those were the two that gave the most trouble. The other one was a very simple math mistake that many made on the question that involved de Broglie wavelength of a particle. You were given the mass of the particle, but you were given it in grams, and you needed to convert that to kilograms. So that was a common math mistake that ended up reducing your score by a point, which is generally what you lose for math mistakes. So if you have any questions on anything else, the tests are finished. I've graded them all, and you can look them over at any point. Okay, so let me pick up where we left off. Okay, I want to, whoops, sorry. Okay. So we talked.
Professor, I have a quick question before you start.
Yes.
Why were there points taken off for the submission of the work?
The submission of the work, what I look for is use of significant digits. Most of you, you were asked for a certain number of significant digits. I think it was mostly 3. I will take off if you submit an answer that's more than plus or minus 1 significant digit. Consistent use of units throughout your calculations. Many of you in your calculations have the habit of entering writing down numbers and not putting any units on it, but then tagging the units onto the answer at the end. The problem with that is that you know what you've been asked for. You've been asked for something in kilometers per second. You've been asked for something in megajoules. Whatever you have been asked for is the unit that you tack on at the end. What you haven't done is verified that you have done all the conversions you need to do. So you miss sometimes the fact that you haven't converted to nanometers when you needed to do nanometers. Your answer was the answer in meters instead of doing the conversion. So I look for consistent units. Everything, even constants, have to have units. Organization of your work. If your work is very difficult to follow because it's not organized, you lose credit for that. So I think it very clearly states what I'm looking for in the work in when you upload it.
Okay, thank you.
Mostly, I'll be honest, most of you lost credit for units. That seems to be the most consistent place where people take shortcuts, is not using units. And we as chemists are very particular about using units. So we talked last time about empirical formulas, but the true formula for molecular compounds is the molecular formula. In other words, it's not the simplest whole number ratio between atoms that matters. What matters is how many atoms are connected in the molecule. So if you look at glucose here, which is C6H12O6, you can look at the mass percent of carbon, hydrogen, and oxygen. And formaldehyde, which is CH2O, and the mass percent of those components is exactly the same. So in terms of percent composition, these two compounds are identical, but clearly they're very different compounds. And the difference between the two is the molar mass. So how do you get the molar mass? Well, in order to determine the molecular formula, you have to either be given its molar mass or you have to determine it experimentally. Obviously, for the purposes of the problems that we're going to be doing, you have to be given the molar mass. So notice that for glucose, C6H12O6, the molar mass is 180.156. The molar mass of the empirical formula, which is CH2O, is 30.031. The molar mass has to be a whole number ratio of the empirical mass. So if you divide the molar mass of glucose by the empirical mass, you end up with 6. I'll point out to you that if you actually take the time to do this math, you will find out that you actually get 5.999. That's because of rounding differences when you calculate these molar masses. You should end up with a number that's somewhere between 5.99 and 6.01 or something like that. You should get very, very close to a whole number. If you get anything else, if the ratio that you get comes out to be something other than a whole number or extremely close to a whole number, then you've made a mistake somewhere. And I would go back and double check the empirical formula that you calculated. Somewhere in the calculation of your mass percents, you've made an error, and it's worth taking the time to go back and check. So let's do a practice problem on this. I will switch my camera here. And we're going to look at this problem right here. A compound of carbon and hydrogen, notice it only has carbon and hydrogen in it, contains 92.3% carbon and has a molar mass of 78.1 grams per mole. You have to be given that. What is its molecular formula? You're going to have to figure out the missing percentage. This is carbon and hydrogen. If it's 92.3% carbon, the total has to come to 100%. That means that the mass percent of hydrogen has to be 7.7%. So we're going to do the same thing we did before. We're going to assume 100 grams. And we're going to take 92.3 grams of that is carbon times 1 mole is 12.01 grams. and that equals 7.69 moles of carbon. The balance of the percentage is 7.7, and that's 7.7 grams of hydrogen times 1 mole is 1.008 grams, and that equals 7.64 moles of hydrogen. This is a perfect example of them being relatively close together, but there's obviously a slight difference, and that slight difference isn't enough. It's based on rounding error. So we divide by the smallest, and we end up with an empirical formula of C1H1. Now we know that the molar mass is 78.1 grams. This is the molar mass. The empirical mass is here is 13. It's 12 plus 1.0, 12.01 plus 1.008. Let me just. This is telling me my battery is running low. I don't know why, because I'm plugged in, but. So the empirical mass here is 13.018 grams. So we divide 78.1 by 13.018. This is the empirical mass. And that equals 5.999 or 6. So the molecular formula is C6H6. It's 6 times the empirical mass, or 6 times the empirical formula. So there is a practice problem. I'm not
Professor?
going to have, yes.
How did you get 13.018 grams?
That's the mass of CH, 12.
Oh, okay. Plus 1.008.
Yeah, it's, I'm sorry, I've just got to plug this in before I lose you all. There we go. I came unplugged. Carbon is 12 and hydrogen is 1.008, so or 12.01. So 13.018 is the mass of the empirical formula.
Okay.
Okay?
Yeah.
Professor,
Yes.
would it be wrong if, because what I did was to multiplied the molar mass of 78.1 by 0.923 and got that molar mass, which was just 72.08, and then divided by 12 and got
No,
6.
that's fine. That's absolutely fine. It's just the longer I teach, the more I recognize that there are multiple ways of approaching problems. And if your brain sees it that way as an easier approach to it, that's fine.
Okay, we're not going to get points off for anything if we take it.
Absolutely not. The method you use, as long as it's logically sound, is fine. It sometimes makes it a little bit harder on me to grade and takes me a little bit longer to grade because I have to get inside the logical approach that you use, which is different than mine. But as long as the logic is sound, there's no reason why you can't use any method that works.
Okay, cool, thank you.
Okay. So let's go back to this is going to do this again for me here. Cancel. It's I don't want to get frozen here. Here we are. Now I'm in the right place. Okay. All right. So there is a problem. I'm not going to send you to the breakout room now. I'm going to send you to the breakout rooms later. Oh, this has done it again to me. It has. I hope that this is not going to make me close out the way I did the last time. But it looks like I may have to. Ladies and gentlemen, I apologize, but somehow when I switch cameras, it freezes me. So I'm gonna end the meeting and come right back. I apologize. I'm gonna have to do that again. At one of the ways, at one of the ways that we use this, one of the more common ways of analyzing organic compounds, most organic compounds contain just carbon and hydrogen, but many contain other components as well, like oxygen, nitrogen, and sulfur, things like that. But mostly they're carbon and hydrogen. So one of the ways of analyzing those compounds is through combustion. Now, this shows you a typical combustion chamber. Let's take a look. Oxygen comes in the end here. Your compound is in this furnace. That is a combustion, by the way. Another way of defining that is combining with oxygens. That's what combustion is. So we take our sample and combine it with oxygen, and it produces, from the carbon in the compound, it produces carbon dioxide, and all of the hydrogen in the compound is converted to water. So we can trap, in this first chamber, you can trap the carbon. In the second one, you trap the water, or we have magnesium perchlorate, and then sodium hydroxide in the last one traps the carbon dioxide. So we can input oxygen, combust our substance, and collect the carbon dioxide and the water and determine the compound's empirical formula. You need to compute the mass of the carbon in the compound from the carbon dioxide that's produced, and the mass of the hydrogen from the water that's produced. If the compound contains anything other than carbon and hydrogen, then you will get oxides of sulfur or oxides of nitrogen. Or if there's any mass missing, if the mass of the carbon and the hydrogen that is produced, or that you calculate from this, is less than the mass of the compound you started with, then that missing mass is due to oxygen in the compound. So you can compute the masses. Once you have the masses of carbon, hydrogen, and oxygen, you can determine the empirical formula. Here's a challenge problem. If you have a 1.000 gram sample of a compound, it produces 2.743 grams of carbon dioxide and 2.246 grams of water. You can determine the empirical formula of that hydrocarbon by converting this mass of carbon dioxide into moles, noting that there's 1 mole of carbon to 1 mole of carbon dioxide, so you can get the moles of carbon in the compound. You convert 2.246 grams of water to moles of water, noting that there are 2 moles of hydrogen per mole of water. So that will give you the number of moles of hydrogen in your compound. And then from that, you can get the empirical formula. If you convert this to mass of carbon first, you can compare the mass of carbon produced and the mass of hydrogen to determine if there's any missing percentage. In this case, if it's just carbon and hydrogen, then you can go directly to the empirical formula. Okay, So,
Professor?
yes,
So when you find the what's it called, the moles of each one, do you just combine them?
no, you're determining the empirical formula. So you do the same thing we did before. You divide by the smallest. You're determining the lowest whole number ratio between the two elements. So
Okay.
you divide by the smallest, you turn them into whole number ratio, just like you did on the practice problems before in determining empirical formulas. This is just showing you one of the ways that we get to the information that you would be given in a word problem. How did you get that information? Probably through combustion analysis.
Okay. So H2O will be separate, then CO2 will be separate, right?
Yes, you
Okay.
collect them separately. Each of those chambers is designed to absorb one or the other. And what they do is they mass the chamber or the substance that's in the chamber that absorbs the carbon dioxide or absorbs the water. They mass it first. After the reaction, they mass it again. The difference is the mass of water produced or the
Okay.
mass of carbon dioxide produced.
Okay.
That's where they get those masses.
All right. Thank you.
Okay. Okay, so we'll go back here. So many of the reactions that we do actually have the substance dissolved in solution. So we need to have a way of measuring how much this, because the solvent usually is water, but whatever the solvent is usually just a vehicle to carry the substance that's actually entering into our reaction. So we're not really interested in the solvent, we're really interested in how much of the solute is present. So we need to worry about how to measure how much solute is present in a given solution. And we do that using the term molarity. Molarity, which is defined by a capital M, is defined as the number of moles of solute per liter of solution. So if you mix 3.4 grams of salt, sodium chloride, which is your solute, in water, which is the solvent, to make 125 milliliters of solution, what is the molarity of the solution? Well, we're going to need a few factors here. We need to recognize that 1 mole of sodium chloride has a molar mass of 58.45 grams. That's going to allow us to get to moles, but we also have to convert this milliliters to liters. So we have 1,000 milliliters is 1 liter. That's going to allow us to convert milliliters to liters, and we end up with 0.465 molar. Okay. Okay, so molarity is a conversion.
Patrick, can you go back for like just a minute?
Sure.
Yeah, can you go back for a second?
Yeah, thank you.
Sorry, I went too fast for you.
Yeah.
Sorry. Is everybody okay?
1 second. Okay, thank you.
Okay. Please note that molarity, or this capital M, is a conversion factor in hiding. And I say that because you're going to use M. It's much easier and quicker to write M than it is to write moles of solute per liter of solution. But you should always remember that that's exactly what that means. So in this problem, how many grams of calcium chloride would you need to make 250 milliliters of a 0.1 molar solution? That 0.100 moles of calcium chloride per 1 liter, or we can actually say 1,000 milliliters. We can combine that so that milliliters will cancel for us. This is going to tell you how many moles of calcium chloride you need. You're then going to need to multiply that, because we don't have any scales that measure moles. Our scales measure grams. So we need to know how much of this calcium chloride do we need to weigh out on our scale to create this solution. Calcium chloride is 110, let's see, it's 1 mole is 110 point, I think it's 58 grams. Let me just check that. It is 40 for the calcium plus 2 times 35.45. Oh, I got that wrong. It's 98. We have to erase that. 98 grams. Moles of calcium cancels. So we would have to take 250 times 0.1 divided by 1,000 times 110.98 grams. You would actually have to measure out 2.77 grams of calcium chloride to make this solution. Okay. Now, you can do 0.1 moles divided by 1 liter and then add another factor that converts milliliters to liters. I did that as one step there. Are we okay?
Yes.
Yes.
Okay. So let's talk about how you get accurate concentrations in the laboratory. First of all, we do not use graduated cylinders to do this. We use something called a volumetric flask. Volumetric glassware is engineered to measure very exactly the concentrations indicated. They don't measure a variety of different concentrations. They only measure one. So what's pictured here is a volumetric flask that is engineered to contain exactly 500 milliliters if you measure the solution to the line that's etched in the neck. The bottom of your meniscus has to align with that line that's etched in the neck. And all of these will say that right up here on the neck, it will say that it is guaranteed to contain that volume at, usually it says 20 degrees Celsius, it might say 25 degrees Celsius, but it's usually at 20 degrees Celsius, which means that at room temperature. So at room temperature, this piece of glassware can measure very accurately 500 milliliters. So you measure out your solute and add it. You add a certain amount of solvent to the flask and you mix that. You don't fill it to the neck yet. You allow the solute to dissolve in that solvent until it's completely dissolved. And then you add more solvent until the bottom of the meniscus is at the neck, at the line etched in the neck. So you might ask, why can't I just simply take that solute that I've measured and add it to 500 milliliters of water? And the answer is that the solute actually occupies some space. And depending upon what solute you use or you're dissolving and what solvent you use, the amount of space that's occupied by that solute is going to vary somewhat. So notice here, we have, excuse me, we have ammonium dichromate, and we have 250 milliliters of water. When you dissolve that and until that meniscus is at the line, you have leftover solvent. So it didn't take the full 250 milliliters to generate that volume of solution. And the definition of molarity is moles of solute per liter of solution, not per liter of solvent. You're going to find out that that makes a big difference in second semester chemistry when we start talking about other forms of concentration. For now, for molarity, just remember that it means per liter of solution. So what about dilution? We often make stock solutions. It would be absolutely impossible for you to maintain a stock of solutions on a shelf at every possible concentration that you might want to use it. So in general, we tend to make stock solutions that are more concentrated than we normally use, and then dilute them as necessary. If we have a 1 molar stock solution, we can have infinite numbers of solution at lesser concentrations that we can make from that solution, and we only have to keep that one stock solution on the shelf. So we take, again, we're using volumetric glassware. In this case, we're using a volumetric pipette that measures exactly to the etched line on the neck of the pipette. We measure an exact amount of our concentrated solution, add it to a new volumetric flask, and then dilute it with more solvent to the etched line on the neck to get a new, more dilute solution. So we've now taken an aliquot, it's that measured volume is called an aliquot, out of our concentrated solution and diluted it to the concentration that we want. So actually, I think I'm going to skip that for now. So let's talk about the math in dilution. The math in dilution is really rather simple. Note that the molarity of our concentrated solution by definition is the number of moles divided by the volume. So if we take that volume and multiply both sides by volume, we have molarity times volume equals the number of moles of your solute. For the same is true for our dilute solution. The molarity of the dilute solution times the volume is equal to the number of moles. When you're diluting a solution, the number of moles of solute doesn't change. All you're adding is more solvent. You're not adding any more solvent. You're only adding solvent. You're not adding any more solute. So the number of moles is the same.
Excuse me.
Yes.
So you said that the molarity equals the moles, the number of moles divided by the volume, and then the molarity times the volume equals the number of moles. But what did you say the dilution was?
A dilution is when you take an aliquot from your concentrated solution, you're removing a certain number of moles of that solute, and now you're adding solvent to it. So what I'm saying is that the molarity times the concentration of your concentrated solution is equal to the number of moles of solute. Molarity times the volume of your dilute solution also equals the number of moles. These two are equal because we haven't added any solute. All we've done is add solvent. So molarity of your concentrated solution times the volume of your concentrated solution will equal the molarity of your diluted solution times the volume of your diluted solution. The general formula is C1 V1 equals C2 V2, or concentration times volume in the first instance, equals concentration times volume in the second instance. Because I had the number of moles is the same. I haven't added any more solute to it. I've only added solvent. So this is the way we do math. If you want to know how much of a concentrated solution you need to dilute in order to make your concentrated solution, you use that formula. And I think we have a practice problem. So I'm going to, whoops. I'm going to go back to sharing to my other camera, and I'm going to do a couple of problems for you. Oops. Okay, so let's see. Okay, so the first one I wanted to do, I skipped this one. This one is on how to calculate molarity of a solution. So we have distilled white vinegar. It's a solution of acetic acid, and this is the formula, CH3CO2H. This is, by the way an organic chemist writes that formula in water. A 0.5 liter vinegar solution contains 25.2 grams of acetic acid. What is the concentration of acetic acid in units of molarity? So let's write the question. How many moles per liter, that's molarity, how many moles per liter equals 25.2 grams of our acetic acid in 0.5 liters. 1 mole of acetic acid is 60.05. Notice I'm not going to show you how to calculate the molar mass. You should know how to do that. So grams cancels, and I end up with 0.839 molar, or moles per liter. So that's basically how to do a simple calculation of concentration. So the next question is, a laboratory experiment
Wait,
calls
can
for,
you go up really quick?
yeah, can I what?
Go up again really quick.
Okay,
Thank you.
I'll leave that while I read the next one. So this is a dilution problem. A laboratory experiment calls for 0.125 molar nitric acid. What volume of 0.125 molar nitric acid can be prepared from 0.250 liters of 1.88 molar HNO3? Okay, so I will always, and I always recommend this, recommend writing the formula. So concentration of the concentrated solution times the volume of the concentrated solution should equal the concentration of the dilute solution times the volume of the dilute solution. That's the formula we're going to use. Or many of you may have learned this as M1V1 equals M2V2. Doesn't matter, either one, it's basically the same way. So let's see if we can figure out what we know and what we need to know. 0.125 molar nitric acid, that's what our target is. So that's our V2, or our dilute volume, dilute concentration. So our molarity in the second instance is equal to 0.125 molar. And we want to know how much, what that volume is, how much of that can we create. So we're looking for V2. We know that we're starting with an initial concentration of 1.8, and we have 0.0250 0 liters. So volume 1 is equal to 0.250 liters. So all I have to do is take this equation and solve it for V2. V2 is equal to M1 V1 divided by M2. And now I just plug in the numbers that I have. It's equal to 1.88 molar times 0.250 liters divided by 0.125 molar. And notice that molarity cancels and we end up in a volume unit, which is what we want. And when we do the math, it's 3.76 liters. So I can create, or I can make 3.76 liters of this dilute solution simply by adding the appropriate amount of solvent. Okay. So that's basically how to do dilutions. Ultimately, you're going to have some problems. I posted a discussion. I would like you guys to get a little practice doing some of these kinds of problems. So I have posted a discussion for you to get some practice with that. So let's go back to this, and I'm going to do some problems with this in a moment, but let me show you that there are a variety of ways of calculating concentrations, and you will see these very often. They'll be noted on the side of whatever bottle or jar that you get something in. So you can get mass percentages. So sometimes you'll have a concentration is listed as mass percent. So it's the mass of your component divided by the mass of the solution times 100. That would be labeled as M/M. You can also have a mass volume percentage where you have the mass of your component. It's usually done as 100 milliliters of solution. So that would be a mass volume. You can also have volume percentages. So volume of your component divided by the volume of solution times 100. So each of these are different ways of doing concentration that you might see depending upon whether your solute is liquid or solid. You can get you'll get different ones. So let me go back and say that we have a couple of problems. I have some sample problems for you that I'm going to show you. The first one is what is the mass of concentrated HCl solution that contains 125 grams of HCl? Concentrated HCl is 37.2% HCl in water, and this is a mass. That means that HCl concentrated is equal to 37.2 grams of HCl in 100 grams of solution. Okay. So I want to know how much or what mass of HCl is contained in 125 grams of solution. So I can ask the question, how many grams of HCl, or how many grams of solution equals 125 grams of HCl if 100 grams of solution contains 37.2 grams of HCl. So I'm using this unit factor to cancel grams of HCl and end up in grams of solution. And it is 336 grams of solution. So if I'm asked to measure 125 grams, or I want 125 grams of HCl to go into my reaction mix, I need to know what volume of this solution to add to get that 125 grams. This is how I would do it. Okay, so that's one way to deal with mass. Okay, so we have another one. This is a volume problem. Wine is approximately 12% by volume ethanol, and this is my formula for ethanol. Ethanol has a molar mass of 46.06 grams per mole and a density of 0.789 grams per milliliter. So the question is, how many moles of ethanol are present in a 750 milliliter bottle of wine? So let's write our question. How many moles of ethanol, CH3CH2OH, equals 750 milliliters of wine? I know that there are 12 milliliters of ethanol. I'm going to abbreviate ethanol as ETOH. The OH represents that OH at the end of the wine or of the formula. So 12 milliliters of ethanol per 100 milliliters of wine. That's our volume percentage. That's going to allow me to figure out the volume of ethanol, but I need to know how many moles. To get there, I need to be able to convert milliliters using density. I need to convert that to grams. 0.789 grams of ethanol per 1 milliliter. So milliliters will cancel. And then I'm going to have to multiply that by 1 mole. Oops, one isn't very, there we go. 46.06 grams. So that allows me to convert grams to moles. When I do that math, I find out that you have 1.5 moles of ethanol in a 750 milliliter bottle of wine. Okay, so that's how you would do volume. Generally, when you're doing volume, you're going to need density in there somewhere. Okay. And I think I have one more that's slightly different. Let's take a look. Okay, so we have here a throat spray is 1.4% by mass of phenol. This is our formula for phenol in water. If the solution has a density of 0.9956 grams per milliliter, calculate the molarity of the solution. So let's write the question. How many, or what is the molarity? I'm going to start this time with density, 0.9956 grams per milliliter. And I'm going to multiply that by 1,000 milliliters because I want to get to molarity. And for that, I need per liter. So I'm going to figure that how many grams there are in 1 liter by simply multiplying by 1,000. And that equals 995.6 grams per liter of solution. Now I have to figure out what the moles is, I'm sorry. And I have to multiply that by 1 mole is 94.108 grams. You can check my math, but that's the molar mass of phenol. And I'm going to find out that that is 0.148 molar. Okay, so if you're going from mass to moles, we need the molar mass. You're going to probably need density somewhere in there. This, frankly, is an example of why you need to write units on everything. You need to know whether you're talking about the mass of the solvent or the mass of the solution. You need to know whether you're talking about the volume of the solute or the volume of the solution when you're dealing with volume. You really need to know. So writing complete units, not just per liter, but per liters of solution, not just mass, but mass of solution. You really need to keep track of your units. When I first started taking chemistry and was presented with some of these word problems, I can admit that I very often was completely confused and didn't have any idea where to go or what to do, and often just looked at the units and asked the units to allow me to figure out what to do. If you have a mass, you can always turn that into moles. If you have a density, you can always turn that into mass if you use volume. So you can use the units that you're given or the units that you know and the relationships you know to allow the units to drag you through the solution of the problem. That's the key. But you can't do that if all you do is write down numbers. If all you do is write down numbers, you're going to end up getting confused. So the last couple of slides on PowerPoint 6, Chapter 6, deal with parts per million and parts per billion. Those are the kinds of units that you will be getting if you're talking about toxic waste, pollutants, things like that. Parts per million, 10 to the 6. Parts per billion, 10 to the 9th. So there's a couple of sample problems. You can do those. Those are on the PowerPoint. For now, I'm going to set you into breakout rooms and ask you to do the two. Some of you actually started the first discussion for today the last time. And I've already posted answers, but many of you, I think only 5 of you did. But there is a second discussion. You can work on that one, which is going to work on some of these other, I think there's a dilution problem, there's a molarity problem, a dilution problem. You can get some practice. So again, I'll put you in breakout rooms and come around and check on, see how you're doing. So here you go. You may join your breakout rooms. First step in most of these problems, Chow, would be converting any masses to moles.
Okay.
Okay.
Professor,
Yes.
are we doing both of them still?
Yeah, you can do both of them. You don't have to do them now. You can post it later. That's fine.
Okay. All right.
Yeah.
Are you okay if I finish offline?
Sure. Go ahead.
All right. Enjoy the rest of your day, Professor.
Thank you. You too.